Today we shall study about electrostatic potential and capacitance. In electrostatics, as shown in the figure, the charge Q is moving from P to R. So the burden by external forces in moving charge is Q from R to P. WRP barabar from integral from R to P F external into dr barabar minus integral from R to P F E into dr. This work done is against repulsive force and gets stored as potential energy. At every point in electric field, a particle with charge Q possesses a certain electrostatic potential energy. This work done increases its potential energy by an amount equal to the potential energy difference between R and P. Thus, the potential energy difference W barabar UP minus UR barabar WRP. Therefore, we can define electric potential energy, the difference between two points, as the work required to be done by an external force in moving charge Q from one point to another point for electric field of any arbitrary charge configuration. So the potential energy of charge Q at a point in the presence of a field due to any charge configuration is the work done by the external force, equal and opposite to the electric force in bringing the charge Q from infinity to that point. Now the electrostatic potential, work done by external force in bringing a unit positive charge from point R to P or Vp minus Vr or Up minus 2R by Q, where Vp and Vr are the electrostatic potential at P and R. It is not the actual value of potential but the potential difference that is physically significant. If we choose the potential to be zero at infinity, work done by an external force in bringing a unit positive charge from infinity to a point, but our electrostatic potential at that point. So potential due to a point charge. Now, as shown in the figure, the charge is at Q and at point P is taken at distance R. P dash point is taken at distance R dash and a small increment distance is delta R dash. Unit charge is 1 coulomb. Is taken from infinity to at point P. Now, work done is bringing a unit positive test charge from infinity to the point P against the repulsive forces of charges Q, where Q is greater than 0, is the potential at that P due to charge Q, as shown in the figure. Now we consider a point charge Q at the origin. We determine the potential at that point P with position vector V from the origin. Work done is independent of the path, as at some intermediate point P dash on the path, the electrostatic work done is independent of path at some intermediate point P dash on the path, the electrostatic force on a unit positive charge is F power Q 1 by 4 pi epsilon naught R dash square in vector R1, where R1 is in vector along OP dash. Work done against this force from R dash to R dash plus delta R dash is delta W power minus Q 4 pi epsilon naught R dash square delta R dash. The negative sign appears because for delta R dash is smaller than 0, delta W is positive, total work done W by the external force is obtained by integrating from R dash barabar infinity to R dash barabar R. This is the W barabar Q bata 4 pi epsilon naught R dash square dr dash integral from infinity to minus R बराबर क्यू बटा 4 पाई एप्सिलॉन नॉट आर डैश from infinity to r, q bata 4 pi epsilon naught r. This by definition is the potential at point P due to charge V बराबर Q बटा 4 pi epsilon naught R. Potential due to electric dipole as shown in the figure. The Q charges at R1, the Q charges and Q minus Q1 charges at a distance dipole at distance 2a, and from Q a point P is taken R1 at R1 minus Q is the distance taken R2, and the resultant distance is R. So we consider an electric dipole consists of two charges, Q and minus Q, separated by a small distance 2a. Its total charge is 0. It is characterized by a displacement vector P whose magnitude is Q to A. R1 our distance from Q to P, R2 our distance from minus Q to P, R our resultant distance. Point potential due to the dipole is the sum of potential due to the charges Q and minus Q. V बराबर 1 बटा 4 pi epsilon naught Q बटा R1 minus Q बटा R2. By geometry, R1 बराबर R square plus A square minus 2AR cos theta, R2 बराबर R square plus A square plus 2AR cos theta, R1 square बराबर R square into 1 minus 2A cos theta by R plus A square by R square बराबर R square into 1 minus 2A cos theta by R. Similarly, R2 square बराबर R square into 1 plus 2A cos theta by R square. By using binomial theorem, we get 1 by R1 बराबर 1 by R1 बराबर 1 by R into 1 minus 2A cos theta by R to the power 1 minus A by 2 बराबर 1 by R 1 into 1 plus A by R cos theta. Similarly, 1 by R2 बराबर 1 by R into 1 plus 2A cos theta by R to the power minus A by 2 बराबर 1 by R into 1 minus A by R cos theta. इसलिए V बराबर Q बटा 4 pi epsilon naught 2A cos theta बटा R square बराबर P cos theta बटा 4 pi epsilon naught R square. Now P cos theta बराबर P dot R, where R into vector R is in vector along the position vector P OP. The electrical potential of a dipole is given by V barabar 1 bata 4 pi epsilon naught P dot R bata R square, where R is very bigger than A. It is true for distances larger compared to the size of the dipole. The potential on the dipole axis theta barabar 0 pi V barabar plus minus 1 bata 4 pi epsilon naught P bata R square. Positive sign for theta barabar 0, negative sign for theta barabar pi. The potential in the equatorial plane theta barabar pi by 2 is 0. Two features. The potential due to dipole depends not just on R but also on the angle between the position vector R and the dipole moment P. The electrical dipole potential falls off at larger distance as 1 over R square, not as 1 over R. Equipotential surface. An equipotential surface is a surface with constant value of potential at all points on the surface. For single charge Q, the potential is given by V over 1 over 4 pi epsilon naught Q over R. It has concentrate a spherical surface centered at the center charge equipotential surface through a point is normal to the electrical potential field at that point, as shown in figure.